Hi, everyone. Thank you for watching. My name is Iyad Rahwan. I'm based at the Max Planck Institute for Human Development, where I'm establishing the Center for Humans and Machines. I will talk today about different experiments in machine behavior, cooperating with and through machines. Just a note quickly at the beginning, I've moved recently from MIT to the Max Planck Institute in Berlin. And we are very much in the growth phase. So if you're interested in postdoc positions, please check out the website, but also feel free to contact me directly. Today's talk will cover three major topics. One is cooperating through machines. So it's about how people could cooperate with one another about how to program a machine. Cooperating with machines. So how can we actually create cooperative relationships with AIs? And finally, I want to close with a broad research agenda about machine behavior. So let's start with cooperating through machines. The canonical example here that I've worked on with my collaborators has been the case of autonomous cars. So the backdrop to this is that just over 1 million fatalities occur every year globally due to traffic accidents. And in principle, 90% of those traffic accidents are eliminatable because the majority of traffic accidents are due to human error. Having said that, people are obsessed with the idea or the prospect of machines making life and death decisions that have ethical consequences. So there is an ethical dilemma inspired by the trolley problem that has become fairly, played an important role in public discourse. And that is the case depicted here, which is a vehicle that's about, let's assume it's a self-driving vehicle in the future, and it's about to crash into a number of pedestrians, but the car can swerve and hit a bystander on the sidewalk, thereby killing fewer people. Should the car commit this act in order to save the greater number of people? And that's similar to the classic trolley problem from philosophy that some of you may be familiar with. But what's different about self-driving cars is that they could also make a decision to harm the person in the car. So the car could potentially swerve and hit a wall, thereby harming the passenger in the car in order to save a greater number of people. Now, we've run some surveys using MTurk with an American sample to try and understand what people think should be done in this case. And as you would expect, especially people in the West, they favor a utilitarian principle where fewer number of deaths is the outcome that's preferred, and people are willing to say, let the car be programmed to swerve, including harming its own passenger in order to save more people. However, when we ask people which car would they buy, they say, I would never buy the self-driving car that would self-sacrifice, but I want everybody else to do so. So this for us highlighted the first kind of departure from the question of how to program a machine from a question of ethics to a question of cooperation. So basically, everybody wants to live in a world where self-driving cars would maximize the greater good, maximize safety, kill the fewest number of people possible in the case of an unavoidable harm. But they don't want to pay the small costs themselves that will bring about this outcome. And therefore, if everybody basically bought self-driving cars that are self-protective, we won't minimize casualties. This looks an awful lot like the tragedy of the commons. It's like a failure or collapse of cooperation in a social dilemma. But when we ask people, well, would you opt into a kind of social contract in which everybody has the same car programming and everybody's car will minimize harm? So you're not the only person who buys the self-driving car that is potentially self-sacrificing in a rare situation, but everybody else would do the same. Would you buy this kind of car? And people were, at least the American participants we studied, were against that. So they would say, well, if you do this, I will not buy the car. I would rather not get a self-driving car. And for us, this is introduces another dimension, which is what we're calling the meta-ethical dilemma here, which is that if you try to impose a solution on the social dilemma of self-driving cars through regulations where opting out is an option, so people could have the option of driving themselves and not buying a self-driving car, then you will potentially delay the adoption of the technology. And if those cars are actually safer than human-driven cars, then there may be more deaths as a result in the interim. Now, we wanted to also understand whether people cared about other factors, not just the total number of casualties. So together with my former student, Iyad, and other collaborators, we built a website called The Moral Machine. And the Moral Machine essentially presents those kinds of binary dilemmas, but with varying a whole bunch of other factors. So this is an example. This is a self-driving car. If the car goes straight, it's going to hit 3 adults and a dog. And the adults are like a male and a female and another female. But the car can swerve, in which case it would hit the barrier and kill one single passenger in the car, who happens to be a female in this case. Notice how the pedestrians in this case are crossing a red light. And in general, we've introduced a whole bunch of factors. So basically, we vary interventionism, the relation to the autonomous vehicle. So sometimes we compare 2 groups of pedestrians as opposed to a group of pedestrians pitched against a group of passengers. We vary the legality of the situation. Sometimes there are no traffic lights, sometimes there are. And we also varied the character type to capture a whole bunch of things, such as perceived social value, perceived life expectancy, age, species, whether it's human or a pet, and so on. And these are the entire set of characters that we used. And what's interesting is when you do this, you actually end up with a multifactorial design that gives you 26 million possible dilemmas. So, which is really difficult to study under conventional psychological methods, like experimental methods using vignettes, for instance. But thankfully, the game became popular, and we got coverage from traditional media outlets such as the New York Times, but also new media outlets such as YouTubers who would play the game, The Moral Machine, and they would have millions and millions of followers watching them play this game and reacting to it and kind of talking through it. And as a result, and as well as the result of translating the game to 10 languages, we got, at the time of analysis, 4 million users answering 40 million ethical dilemmas and filling more than 500,000 demographic surveys at the end. Now, since we've actually analyzed the data, this particular snapshot of the data, the numbers more than doubled. And we've made the data set available for others to analyze, and I want to share with you now some of the results. So first of all, let's see the geographic coverage of the experiment. And as you can see, it's fairly broad. We have very high resolution when you geolocate the users. And in fact, this looks a whole lot like the map of the lit world. So there's even the empty spaces are actually in large part uninhabited spaces. And to get a sense of what these questions look like, let's go through a few examples. So this is a question asking, what should the self-driving car do? Should it go straight or should it swerve? If it goes straight, there would be two casualties in the car. If it swerves, there would be these 2 pedestrians would die. Now, I want to invite you to answer in your head before you see the result, just to test your intuition and see how you compare. In this case, indeed, more people would say go straight and kill the passengers. So there seems to be some kind of bias to favor pedestrians. Now let's look at this case. It's an empty car going to park itself, for example, and it's about to hit one child, but it can swerve and hit an adult. What do you think should happen? How do you think the car should be programmed? Indeed, most people would say the car should swerve, although not everyone. So some people prefer the car to just go with the default. What if the car would swerve to kill a jaywalker in order to save somebody who is crossing legally. And in this case, more people would say swerve, like a substantial percentage of people would say the car should swerve. But then suppose we add one more jaywalker. So now we're pitting two values against each other. On one hand, saving more lives, and on the other hand, saving the person who hasn't done anything wrong. And in this case, people start, the decision becomes more difficult and people are kind of split in half. I want to show you here the results from the entire, the analysis of the entire data set using conjoint analysis. And here what this plot shows is the change in probability of saving an actor, let's say an animal or a person. If you replace the thing on the left-hand side with the thing on the right-hand side. Now, as you can see, if we take an animal and we replace the animal by a human, the probability of saving the human goes up by 60%. Saving more people is also a very important factor. So the probability goes up, for saving 2 people versus 1, or 3 people versus 2, and so on. And these are the remaining factors, and some of them are kind of surprising. For example, preference for sparing pedestrians is there, but it's not as strong as some of the other factors. Also notice age, for example, is very important, saving children, which seems to actually contradict with some of the early guidance provided around self-driving cars and the risk distribution. Notice also here the sparing lawful people is about equivalent to sparing higher status people. So, you may very well agree with sparing people who are crossing lawfully, but you may not agree that we should have a policy to spare higher status people like business executives, for example, over homeless people. So this is a case which invites us to reflect over the value of crowdsourcing or public polling of preferences, because we don't necessarily take those preferences as a direct and translate them directly into policy. Some things maybe make sense, others would violate fundamental rights and so on. But what's really fascinating about the game and the scale that the game has grown to is that we're able to repeat this analysis at the level of country, which enables us to compare countries, but also measure the distances between them. So you can see here that we've got, these are the effect sizes plotted on a radar plot. You can see, for example, sparing humans is the strongest. These are all compared with one another, basically compared to the minimum here. This is no effect size. And let's take 2 countries to compare. Let's look at Germany, for instance. You can see that Germany has a stronger preference than the global average for sparing humans, substantially stronger preference towards inaction, towards not intervening, and lower preference for sparing higher status people, which you could imagine makes sense because it's a fairly egalitarian society. And look at what China looks like in comparison. So there's really there's some agreement with Germany, but there's also some significant departure. For example, preference for sparing the young is there, but it's significantly weaker than the global average. And if you do this exercise for all countries and runs a clustering algorithm on them, you get a clustering dendrogram that actually looks fairly in agreement with cultural classifications that have been basically arrived at by anthropologists. You could zoom in here, for example, and see the Western cluster. Even within the Western cluster, you could see that Protestant countries bunch up closer to one another, and for instance, English-speaking countries cluster together. You could see in the Eastern clusters a lot of Muslim countries and Southeast Asian countries. And in the Southern cluster, you could see here South American countries clustered together as well. Now, does any of this matter? There is an elephant in the room, I think, that I need to discuss quickly, which is that, well, these scenarios are so rare that they're not going to ever happen. And we've written some longer pieces discussing this issue, but very quickly, I think the trolley problem acts as an abstraction. It's an abstraction of some ethical dilemma that is much more statistical in nature. So let's imagine a vehicle, self-driving vehicle, that's driving along a lane, and it needs to decide about where it should position itself in the lane. Should it get, and in this case, there's a truck on one side and there's a cycling lane on the other side. So the car could choose to be a little bit further from the truck and closer to the bike, or it could be a little bit further from the bike and closer to the truck. Now, and perhaps millions of cars would be programmed to the same behavior. Now, you could imagine that in a single instance, nothing would happen. There is no dilemma. But over millions of instances of this type of scenario, perhaps leaving a lot of extra room for the bike would slightly increase the probability of an accident involving the car and the truck with passenger fatalities. But if the car leaves extra room away from the truck, there may be an increased probability of a crash with the bicycle over millions of instances. And you can imagine this happening for overtaking and leaving, how much space does the car leave in front of it versus behind it, and under what conditions do you merge, and so on. And indeed, this kind of logic has already been described in some of the patents for self-driving cars, where risk penalty is calculated based on the probability of events happening and a risk magnitude that captures the potential cost of different types of accidents. For example, hitting pedestrians who run into the middle of the road, or being hit from behind, and so on. Now, so that was the question of how do we, as humans, agree on how to program a machine, so cooperating through the machines. Now I want to talk about a couple of other projects in which we've investigated the possibility of cooperating with machines. So a lot of the progress in AI has been really driven by zero-sum competitive games. So for example, chess is a zero-sum game. One player loses and the other player wins. Go is the same, and so is poker, and even Jeopardy as well. There's a winner that takes all of the money. Now, these games happen to be fairly simple in some respects. So they're very obviously that they have combinatorial complexity, but they're fairly simple in that minimax guarantees you the optimal strategy. It's a very old result in computer science. In terms of cooperation with machines, we do have research on human-machine collaboration, but normally it's collaboration by design. So the machine is designed to collaborate with the person because it's kind of in a subservient role. For example, it's working in a machine shop with a human, and it's providing tools or helping the human perform some task. We're interested in situations that look more like the prisoner's dilemma. So a situation in which I'm interacting with the machine. This machine has different goals. Perhaps it represents other stakeholders, other users online, for instance. And the question is, could this machine figure out how to cooperate with me, even though it doesn't have to, because it's not under my control. So what we've done is we've taken the classic approach to studying cooperation, voluntary cooperation, namely the prisoner's dilemma. This is a case where everybody, there's two players, each player has a resource. They play simultaneously. The person can give this resource to the other player, which is more valued by the other player. And the best outcome happens when both players exchange favors, thereby improving both of their utilities. But the collapse of cooperation happens here because there is a temptation to keep what you have, but also take the thing that the other person is giving. Now, what we've done is we have, together with Jacob Crandall, my collaborator on this project, we picked an algorithm called S++ that he developed. It's a meta-reinforcement learning algorithm based on expert algorithms. I'll explain that in a sec. But it's an algorithm that's able to play generalized repeated games very successfully. It has a number of properties, so it's not just any algorithm. It's nice. So for example, it never initiates defection in the prisoner's dilemma. It's lenient. It's robust to small deviations. If the other player makes small mistakes, it's not going to trigger, for example, like a grim trigger strategy that will over punish. It's also forgiving. It returns to cooperation after punishing defectors. So it does punish, but it does return to cooperation fairly quickly. But it also has this other really important feature, which is that it converges, at least in self-play, when the algorithm plays against itself, it converges very quickly to a cooperative equilibrium. And this is a comparison of different reinforcement learning, like some of the state-of-the-art reinforcement learning algorithms playing the prisoner's dilemma. You could see that many algorithms actually end up with mutual defection completely, either quickly or eventually, including deep Q learning, an implementation of deep Q learning algorithms. But you notice here that some algorithms do reach cooperation, but after many, many rounds, so 10,000 rounds of play, which is completely impractical when it comes to running human subject experiments. So S++, as you can see, actually converges when it plays with itself fairly quickly in just over 10 rounds. So, I don't want to get too much into the details of the algorithm, because it's beyond the scope here, but it's a meta algorithm that uses a whole bunch of other algorithms, and each of these sub algorithms decide how to play, and then the meta algorithm picks one of those sub algorithms as the one that's being used now. But they're all, it's like multiple perspectives on the game that's going on. So in addition to S++, we also introduced S#, which is the same as S++, but has the ability to generate signals or cheap talk. And these are not like complete natural language generated, but they're pre-programmed responses. For example, you will pay for this, or I will punish you, or, let's make money, or, if you play this, I will play that, and so on. And it has, this is the finite state machine that is responsible for controlling this signal generation and interpretation. And just want to show you one of the main results we have is, this is in different games: alternator game, chicken, the game of chicken, and the prisoner's dilemma. Alternator game is a kind of coordination game in which cooperation is achieved by taking turns. You could see here that, and this is with and without communication. So without communication, basically in a human-human play, people always do better if they can communicate. And this is kind of known even in the prisoner's dilemma. So you could do much better than the baseline in terms of mutual cooperation if you can communicate. But what's interesting is that, so here we have the human versus S#. S# is able to eventually achieve human level cooperation, close to it, in the game of prisoner's dilemma, and does very well in the alternator game, in the game of chicken. And here you could see S# against itself. It's actually able to cooperate even better. So in a world where there's humans and algorithms, maybe the algorithms will just choose to play with each other and not with us. I want to show you here some of the differences, behavioral differences between the two. So here you see that people find both the machine, the algorithm, and the human equivalent in terms of their intelligence and intent, at least in this particular game. However, they can tell better than random that it's an algorithm. It's also interesting that even though the algorithm achieves levels of cooperation comparable to the human, they do this through different signaling behavior. So for example, they praise less and they threaten more compared to human players. Now, I want to move, then subsequently we'll move to another question, which is, should bots reveal their true identity? What happens if we hide the fact that this is a bot that you're playing with? And this question is actually relevant because a couple of years ago, Google released Google Duplex, which is this voice assistant that can undertake extremely realistic conversations, including umming and ahhing. And people were impressed by it, but it also caused some outcry. For example, the Washington Post published this title, "Google program can pass as a human on the phone. Should it be required to tell people that it's a machine?" The Guardian here is reporting that Google's deceitful AI assistant will be identifying itself as a robot during calls. So this is what Google's reaction to the outcry. And more recently, just to make things a little bit more contemporary, Google Duplex has been calling businesses to check the availability of critical products, for example, like toilet paper. So this is actually ongoing, so it's being used. So what we've done in a follow-up paper is we've varied the information that we give to participants. So sometimes they played with a bot, and we told them it's a bot. Sometimes we played with a human, but we told them it's a bot, and so on. So all 4 combinations. And what's interesting is that at the beginning, depending on whether we told people they were playing with a bot or a human, there was only a slight increase, but this was not statistically significant in the probability of cooperation with a human compared to a bot. But in the second round, this is after the associate has cooperated in round 1, people were less likely to cooperate with the bot. So perhaps they thought they could, this bot is a sucker, we can exploit it. And also if the opponent defected, they're also more likely to defect against the bot. Perhaps they thought this bot is a defector, it's dumb, I don't want to trust it, right? And something similar happens in most cases in the third round as well, independent of the play of the strategy combination in the first 2 rounds. And overall, this table shows that participants are always more likely to cooperate with a purported human, regardless of their partner's decision history. So in round 2 and round 3, people are always more likely to cooperate with the human than with the bot. So there's a kind of bias against cooperating with the bots. And you can see this here. So you can see that this is the case where the associate is a human. And if people thought they were playing with a bot, even though they were playing with a human, they were less likely to cooperate. So they were interpreting the same behavior of the humans differently. And this is the case where the associate is a bot. It's interesting that unlike the case where on the left, when the associate is a bot, the bot is actually able to recover some of the cooperation, but only if people believe that they were playing with a human. And even debiasing people, attempting to debias people by telling them, you're playing with a bot, but we suggest that you treat it as a human, that was not sufficient to overcome this bias. And what's interesting with bots is that we can look inside their heads. We could look at how they were perceiving things. Unlike, maybe this is equivalent to like an MRI study with humans playing prisoner's dilemma. You could see that the bots are learning quickly to expect less from humans compared to other bots. Okay, so now I want to just quickly cover a research agenda on machine behavior that takes these projects to a broader context. And basically, we wrote a paper, a review paper that was published last year, trying to define what we mean by machine behavior. And this paper was co-authored with a whole host of computer scientists, as well as behavioral scientists and biologists. And the idea is that lots of questions about the behavior of machines can be studied behaviorally, not just algorithmically, by doing computer science analytical studies. Questions about news ranking, algorithmic justice, questions about autonomous vehicles and autonomous weapons, algorithmic trading, algorithmic pricing, online dating, and conversational robots can all be studied behaviorally. So instead of just certifying machines as ethical by looking inside their heads, looking at the source code, we could potentially study and certify machines by looking at their behavior, just like we do with humans. With humans, we don't certify them as ethical by opening their brains and understanding how their brain functions necessarily. We do it behaviorally. So this is similar to if you like, the study of animals, the behaviorism of animals. We can imagine an AI as an animal that can be studied by looking at the source code, but also can be studied by putting it in a controlled environment and subjecting it to stimulus and measuring the response, the behavior. For example, you adjust the heat, the temperature, and then you look at this its impact on sleep. So you could do something similar with a machine. But you could also go beyond just controlled lab behaviorism. You could do more ecological studies as well. So the idea is once you could do this, then when people present their algorithms, you have behavioral tests through which you can compare these algorithms and not just proven properties. This actually happens to be an old idea that goes all the way back to Herbert Simon. In his book, The Sciences of the Artificial, he asked whether, in contrast to a natural science, can we have artificial science, which explores knowledge and builds knowledge about artificial objects and phenomena. And of course, you don't study machines in isolation. You study them also collectively because they have emergent behavior, and you study their interaction with humans in a complex system. And this is how we think machine behavior relates to other fields. So it basically lies at the intersection of the behavioral sciences and the engineering sciences of AI. What we've done in the paper, and I won't get into the details here, is we've taken a lesson from biology, namely the Nicolaus Tinbergen, who won the Nobel Prize in medicine together with Karl von Frisch and Konrad Lorenz for founding the field of animal behavior. And what we've done is we've taken the 4 fundamental questions of animal behavior in biology, which have become an organizing principle for studying biological organisms in general, and we've translated those to the study of machine behavior. And I invite you to look at the paper for more details. So let me wrap up here. This was my alarm indicating that I'm out of time. So in summary, we've looked at some projects about the question of human-human cooperation through machines. And we've seen that programming AI gives rise to public goods games, cooperation dilemmas. We also saw cross-cultural differences in the ethical values that might shape these kinds of agreements between humans. We've explored the question of cooperating with machines and so that emergent human AI, like voluntary emergent human AI cooperation is feasible. But there are trade-offs between transparency and efficiency, at least for now, because of the view that people have now of AI. And finally, I've tried to outline a research agenda for AI as the object of behavioral study. And I want to add here that the computational social science community is especially equipped to lead in this regard, because we have a lot of behavioral scientists who are very technical and are not intimidated to run experiments with AI algorithms. If you want to learn more about any of these projects, here are the relevant papers. And finally, I want to thank all of my collaborators on these papers who've really made all of this work possible. I could not have done it without them. So thank you all, and I hope you learned something useful.